Okay, so today, element quiz, rocked it. You guys, I am not a nice guy, but I'm super impressed with you guys already this year. You turned in your homework in advance, quite a few of you. Now I know there's some of you that didn't even, you're like, what? Probably haven't even accessed the Canvas course yet. But overall, most of you are on task, and that's a really thick pile of paper right there that did really well. So keep it up. You guys are awesome. Okay, whoops, I forgot to change this part at the bottom. This is, I just cut and pasted from the first time. Okay, don't, but please do. Oh no. Could be in trouble today, we'll see. All right, so it broke itself. Don't worry about this. The rest is changed. I just forgot to change the blue. And then, what am I doing wrong here? Okay, let's just jump into units of measure. These are review, I hope. Oh no, this is not what I want. This is what I did last year. Okay, we'll see here. You don't need to write all these down. We're going to use them throughout the year. But here are some units that we'll use in this class. We definitely will use grams and kilograms a ton. So these are the SI units, or the System International units. It's the metric system. You've heard of it before. So for mass, we use kilogram or gram. For length, we use meter or centimeter or millimeters or nanometers. We use that a lot in this class. Time is just seconds with a S and then the little A. Don't worry about that yet. And then temperature, in this class, we'll use Kelvin most of the time. You've heard of Fahrenheit. We never use that in real science. You've heard of Celsius. We'll use that occasionally, but most of the time we will use Kelvin. Kelvin is a true scale that goes to an absolute zero. This is probably not going to write. Oh, well, that's progress. Nope. Okay, you should know the following, that the difference, oh my laws, the difference between 30 degrees Celsius and 31 degrees Celsius would be the same difference between 30 Kelvin and 31 Kelvin. Now, they're not the same temperature, but it's the same amount of change between each temperature. Okay, so the change is the same. They're just not exactly the same. To go between Celsius and Kelvin, you take the Celsius number and you add 273. Now, let me close this program and open it up and see if my marker will actually work. This is what it started to do at the end of the year. This is when this slate accidentally got thrown into the wall at a high rate of speed. Don't worry, it was cool. No one was hurt. Some people cried though. It may have left my hand on accident. It's just one of those days, kids. It fell out of my hand on accident. Now it it comes apart. Well, how many of you get frustrated with technology quickly? Anyone? Because it works fine until it doesn't. And there's zero explanation to why. It's just like, okay, bro, I'm done. And then for some reason, it just teleports to one side of the room. I'm never sure how it Yep, exactly. But if there's a wall on the way, then you got a problem. Yeah. Okay, cross your fingers. Yes. Okay, we'll see how long. Holy cow, where are we? Okay, so we'll see how long. So Kelvin is equal to Celsius plus 273, and technically it's whoops, you'll see why I did that in the future. Technically it's 0.15, but I don't stress on the 0.15. You may see that in a college class. I don't know. Did your professors ever care about the 0.15? Yeah. Oh, wow. So we're backwards. That's why they get 5s and you guys get 3s. Not funny. Thank you. Okay, Kelvin. Anyway, a mole. Kids don't like moles in chemistry, but it's just a word that means a really big number. We'll go over that a ton. So in chemistry, when we have an amount of substance, we usually call it a mole. And we will spend tons of times talking about moles. All right, electrical current. We do not talk about that till the very last unit. It's called amps, and there's the abbreviation. And then honestly, in AP chemistry, I've never once talked about illumination and candelas. In physics, you do a ton, but whatever. We may come across other things, but these are it. We're going to have a whole slide about volume here in a minute, so don't think I forgot that one. All right. The metric system is great because it's just multiplying or dividing by 10. It's moving the decimal, and I think that's way easier than doing fractions between halves, fourths, eighths, 32nds, and 64ths personally. But anyway, we will spend most of our time with kilo, milli, and nano in this class. So we have our base, and then it goes up or down based on what the prefix means. So like centi, it means it's 1/100th. Milli, 1/1000th. Kilo, 1,000 bigger. Nano, that's the only real small one we use. It's 1 × 10⁹. It's a billion. So it's pretty small. All right, you don't have to memorize these anymore. In 2013, they took a ton of the memorizing of minutia and they took it off the AP test. But you should get used to being able to at least convert from the standard, like a gram, to a kilogram or a milligram. Okay. Volume is actually a really complicated idea, but it's fine. The most commonly used metric unit for volume is the liter and the milliliter. A liter is a cube 1 decimeter long on each side. Okay, that's what that is, but who cares? This is what I want you to worry about. A milliliter is a cube that's 1 centimeter by 1 centimeter by 1 centimeter. So if we drew a square that was 1 centimeter on each side, it would occupy the volume of 1 milliliter. So centimeter cubed and a milliliter is the same. And we will use this a ton. You'll need to be able to convert from a liter to a milliliter and vice versa all year long. That's coming up in chapter 4, so we'll focus on it when we're in chapter 4. But you either move it 3 left or 3 right. This is usually not something you struggle with. Just know that it's coming. All right. Now, uncertainty in measurements. This is a pretty important concept in AP. Every AP test question free response part is worth 9 points. And one of those 9 points is just simply writing the answer with the right significant figures. Sometimes it's 3 of the 9 points. It's like, what? I can get 1/3 of my points just reporting it to the correct number of digits? Yeah, you can. All right. So uncertainty, when we report an observed value, like a measurement, the way we report it will let the reader know how accurately we measured it. And the way you do that is by how you write the number, how many digits you put. The more digits you put, the more accurately you are stating you knew the number. Okay? If I say that I have around 30 kids in my room, that means I probably don't know exactly how many kids I have, but there's around 30, right? And if I say I have 32 kids in my room, that usually means I know I have 32 kids in my room. One's vague and one's not vague, right? All right, there's vagueness built in or accuracy built in to how we report our measurements and how the tool we used can be reported by just writing the number. All right, so anyway, different measuring devices have different uses and different degrees of accuracy. So a volumetric flask You would never use this to really measure anything except for, and you can't see very well, on a volumetric flask, they are made for one measurement. There'll be a line etched in the glass, and you can measure pretty close to that line. But if I wanted you to get me 50 milliliters of stuff, you would never use this. There's no lines. If I wanted 50 milliliters of stuff, I'd come over here, and there's 50 and 40, and then the lines between. Like, I would use a tool that's more accurate. If I was getting a shot where whatever I needed to be exact, I'd want a very narrow tube with lots of lines so I could get exactly the right amount. Burette is basically an upside down graduated cylinder. A pipette, we don't use that style. We use these, and ours are not used for measuring. They're just there to transfer stuff. That glass pipette would have graduations or marks on it. But anyway, moving on. Okay, we'll talk a lot more about significant figures and accuracy and measurements coming up in a second. Temperature. Temperature is a measure of the average kinetic energy of the particles in a substance. So it really is measuring how hard the particles are hitting the thing you're using to measure the temperature. We'll talk a lot. I mean, all these are used all throughout this year. Okay. Oh, I kind of already said this, but I guess here's a slide for you. In scientific measurements, the Celsius and Kelvin scales are most often used. The Celsius scale is based on the properties of water, where 0 Celsius is the temperature at which pure water freezes, basically. And then 100 is where it boils. And it gives us a nice reference point because there's a lot of water on this planet. But Kelvin is a scale that gives us an absolute 0. There's nothing colder than 0 degrees Kelvin. And then there's just that conversion again. If you're at 0 Kelvin, you're at 273. Boiling is 373. This is the number you'll use way more often than any other value. And it's 298 degrees Kelvin, and that's considered room temperature. So that's around 72-ish degrees Fahrenheit is what they consider to be room temperature. And we'll use that number a lot because most experiments or things we'll read about are done at room temperature. So we just throw in the 298 and we're ready to roll. All right, you all right with that? Okay, I just keep repeating myself. The Kelvin is the SI unit of temperature. It's based on the properties of gases. There are no negative Kelvin temperatures. So don't ever, if you do math and get a negative Kelvin, then you have a problem. Yes. That's a super good question. We don't know. And it's kind of unique. You know, you ever seen the old piggy banks where you can put it in, but you can't take it out? How would you know how much money you had in there? You have to break it open. Do you have your piggy bank anymore? No, so you can't know and have the piggy bank at the same time. In order to measure absolute 0, we need to use some sort of temperature probe, which introduces its own temperature when we put it into that environment. So we probably have, but we haven't found a way to prove it yet because our tools break it at the same time. Fair enough? Okay. So anyway, I've said it 10 times. It's plus 273. By the way, you will see this. You will see delta, and it equals a negative 2.8 K. That does not mean we have a negative temperature of 2.8. That means that the change, that's what delta means in chemistry. The change in temperature decreased 2.8 Kelvin. Okay, so there will be some answers in this year where you put a negative and then a K, but that's because it's the change. So if it was 50 and now it's 48, the change was negative 2 Kelvin. So anyway, don't panic if you see that. All right, the Fahrenheit scale is a waste of time and not used. It's Fahrenheit equals 9/5 Celsius plus 32. Who cares? All right, density. Density is important because it's on the test. And it's really the only math that's on the test. And there was some density problems on the homework, I believe. The homework said it was due on the 6th. I changed that to the 9th. So tomorrow night, because we hadn't gotten to this part yet. But if you already did it, great, which is over half of you. All right, so density, it's a physical property of the substance where we take the mass divided by its volume. All right, then I like to teach this little circle. I call it the Tom circle because I love talking about myself. How many of you have ever done algebra wrong and it was just dumb that you did it wrong? Anybody? Okay, I did it a lot. And finally, when I was in college with my physics classes where there's 200 3-variable equations, someone showed me this and it saved me a lot of pain. Any 3-variable equation can be put into this style of a circle. So you take density equals mass over volume, you take the variable on top of the fraction and you put it on top of this circle. Then you take the other 2 variables and you put them on the bottom of this circle. Okay, so write this in your notes real fast. This is density equals mass over volume. I'm going to turn this on. Is that all right? Okay, you'll like it. Okay, now how this works, if 2 numbers in this circle are next to each other, you multiply them. If 2 of the letters are on top of each other, you divide them. Okay, now the way this works, you cover up in the circle the variable that the problem asks you for. So if I cover up D, if I want to know density, I'm left with mass divided by volume. Fair enough? Now, if the problem asks me for volume, I cover volume up and I'm left with mass divided by density. If I want to solve for mass, I cover mass up and I'm left with D times D. You all right with that? This is just doing the algebra for you. Most people are fine. If I say solve for M, they're like, oh, easy. I multiply V by both sides. You're good at that. If I say solve for V, that's when you screw up because you got to take V over and then D back under. And kids get that wrong a lot because they do it fast in their head and they do it incorrectly. So use the circle. So when asked for density, mass over volume. Volume, mass over density. Mass, density times volume. You okay with that? It's a pretty simple concept. But anyway, you'll get to use this circle a ton if you ever take physics. All right, now back to uncertainty of measurements, and we will apply this to density coming up here in a minute. All right, significant figures. This is how we report how well we know our answer. And this is a huge part of this class. So if you paid no attention to anything yet, at least pay attention to this part about significant figures. So significant figures, the term is used to refer to digits that were measured. So it's not like the score of a football game. It's not your grade. It's something that we went and measured in the lab. And when we report that, we need to be very specific how we report it. Okay, so when we round calculated numbers, we pay attention to significant figures so we do not overstate the accuracy of our answers. This is all going to come together, I promise. And then the real definition, it's not like the science one, it's my definition. Significant figures are all things that we know, and then we make a guess. Now, what does that mean? Well, let's use an example. So, Mr. Stacy, Davis, will you stand up for a second? Okay, in your lives before, You have looked at someone and wondered how tall they were, right? Look at this young man and will you guess his height in your notes? You can sit down now. All right. Thanks for making eye contact with me. Danielle, will you stand up? Will everyone guess her height? Okay, go ahead and sit down. I don't know if did I spell your name right there? Okay, close enough. Okay. How tall are you?
I think 6'4".
6'4". Okay, now just let's think about this. I'm looking at Seth. Seth put 6'1". That's fair. All right. How many people put 6'4". Just him, right? How come you put 1/4? He went to the doctor. He knows how tall he is. Do we? No, so we guessed. How many people put 6'4"? Nice job. 6'3", 6'2", 6'1", 6'0", 5'11". Oh my, wow. And so, yeah, it's okay. Did anyone go lower than 5'11"? Anybody go higher than 6'4"? Okay, almost all of us, and it's okay. We're able to know that he's tall. And in America, we define tall with what usual number? A 6. So when we are thinking about a measurement and reporting it, it's all we know and a guess. I think that it's pretty easy to know he's above 6 feet, but that's because I'm pretty close to 6 feet and I definitely have to look up to him. Yeah, can't relate. The shorter you are, the harder it is to guess someone's way high height. Okay, good. All right, Daniela, height. 5'8". 5'8". Okay, how many guessed 5'8"? 5'9", 5'10", 5'11", 6'4". Everyone guessed a 5, right? All right, how many 5'7"s? 5'6"s? So you're 1 inch off this time, and you're probably around 5'8" yourself. Well, how tall are you? Yeah, you're right there. So it's pretty easy to estimate her height because you're close. All right, but no one guessed 4 feet something, right? And that's because you're kind of tall for a girl actually, but you're definitely not over 6 feet. Everyone here knows you are not 6 feet tall. And no one on the planet would guess you're 4 feet something, right? It's what we know. We went, hey, she's got to be 5. She's not a short 5. She's a tallish medium 5. And almost all of you are within 2 inches, were you not? Okay. When we report a measurement, we do this exact thing. We look at the tool and we find what we know, and then we add one more number that's a guess. Now, it's not a guess, it's an estimated guess. Now, I love that David said he's 6'4" and 1/4. When we report a significant figure, if someone said, how tall is that kid? And you said 6'4" and 1/4, you're implying that you really know, because you're like that far off of being wrong. If you say, I don't know, 6'4", well, then you're like, well, he could be anywhere from 6'2" to 6'6", right? We don't include these unless we know them. It's everything we know and then one guess, not more than one guess. Okay, good, thank you. And as we do these activities, hopefully the height analogy will sort of make sense. So looking through here, we have, oh, this is huge, hold on. That's too small. Got Goldilocks right here. Okay. So we have a picture. This is a picture of one of these. It's a quadruple beam balance, and it's just showing you where the things are pointing. When we look at these measurements, we report what we see by listing everything we know and then a final digit that we estimate. So if I look up here, I will notice, or you will notice, that there's 186. And is that all we know? No, there's another slider right here. So I have 186. I know that for sure. I look and I know it's between 0.6 and 0.7. I know that. And then I look right here, and it might be harder to see, but that one's right there. It's between the 8th mark and the 9th mark, right? So I know it's 0.68 something. Do I know anything else? No. So then I estimate what this last digit is, and I'll just say it's right in the middle. So this measurement, looking at it, significantly reporting it, I would report all the values that I knew, and then one more that's a guess. Now it's kind of strange, but why this is important is if someone reads this number, they know the accuracy of the scale you use. And that's important in real chemistry. If we use something accurate and report it accurate, then the reader knows it was accurate. If you just put this is 186, well, that would mean this whole part didn't exist from here on. Is that very accurate? No, we knew it much more accurately. 186.6, then this part didn't exist. 186.8, then that means there were no lines between 0.6 and 0.7. All right, and then there were, so that's why we went to 3 extra digits. So when we report things, we have to report everything we know and then a guess, which we estimate. Okay, ooh, that's really hard to read, but this is 20, 21, 22, 23, 24, 25. And we're going to measure from the bottom of this curved thing, which we call the meniscus, which is a little bit below 25. Will you write your guess of what this measurement would be and report it using the correct significant figures? All right, will you glance at your lab partner and see if you guys match? And it's, you don't have to have the exact number. I want the exact same number of digits. What you got, Sky? You running today? So you two are the same and you're not the same. You better figure out which one's right.
Oh,
Always give up.
no.
That's very inspirational. You guys match?
Yeah.
Where did you write it? Holy, let me get my glasses out. I would guess it's around that. What?
Or is that your height and you?
No, I coach the high jump. And so that's how high people have gone.
Okay.
All right, here we go. The correctish answer is 24, and that's what I know, right? And then I just estimate it. 24.9, great. 24.8, great. 24.95, wrong. 24.95 would imply, and I know you're like watching this like, who gives a crap? Well, science does, okay? 24.95 implies that this graduated cylinder has those lines right there, but it doesn't. So we can't overstate the accuracy of what we're doing. Okay, I think there's one more. Here we go. See if you can get this one. This is different, right? Yeah, it is. It is. You can do it. Whoever said that was good. Don't always give up. Okay, same deal. Check with your partner real fast, see if you guys match. Remember, the last value doesn't need to be the same. The rest of them should be though. You gonna sneeze? Okay, good. Got it?
I got it.
Nice. Okay. So here we go. My lab partner here has 135.413. Did I read that right? Who agrees that that is a correct answer with the correct number of significant figures? Okay, that wasn't a lot of hands. Oh, never mind. They're just lower. Okay, this is a correct answer. There are more of them. 135.412, grand. 135.411, perfect. All that with a 4 at the end, great. But this would be wrong. That would be wrong, right? Because we do know this value, which means we have to have this one. Okay, now, last one. This one is kind of weird looking. That picture's not the best picture ever. This is the 8 right here. This is the 7. This is 7.1, 7.2, or sorry, 8. I don't know, sorry. 8.1, 8.2, 8.3. Teamwork. Are we out of here in 2 minutes? All right, here we go. 8. We know it's 8 no matter what. We know that for sure. We do know one more thing. It's a little bit below 2, so it's a 1. We don't know where, so we estimate, and it's pretty high, right? So I'd say a 9 or an 8 right here. We feel okay about that. How many had that right, if you're willing to admit? Had it correct? Higher, because I'm sitting down. All right, moving on. You don't have to do this. I feel like we've done enough. All right, there's the lab. Here we go, here we go, here we go. All right, so why do we care? Are we out of here in 1 minute? Okay. I am going to put this out on an announcement and ask you to watch it. You on campus, because it is interesting why we actually care. Okay, if you haven't done all your practice problems, please do them. We do have just a little bit of stuff to do tomorrow. There's like 3 more slides is all. Homework? Not if you already did the ones from the other day. All right, Zoomers, if you have a question, hit the chat real fast. Thank you. Yep. Yeah, I want you to take it. All right, I don't see any chat, so I'm just going to end the meeting. You guys are awesome. Sorry, you're at home.